Dear stress engineers, we are coming close to the end. So chapter 14 deals with dynamic analysis, meaning not the normal natural frequencies that we have already discussed in chapter 4, but exactly the response of a structure to dynamic forces solicitation. So we still keep the same example, same beam, loaded in a different way, and we go first of all through the frequency response, where we can then extract by changing the frequency of the forces. We can see that we pass through one resonance, of course, and we see also the phase angle which at resonance changes. Then a comparison with let's say approximation on how this could be obtained by static analysis is given. Then solution techniques are discussed. So what kind of solution can be used? There are mainly two different. One is the direct integration, so the equation of motion is taken as it is and integrated directly, step by step. And the second one is the model superposition. Anyway, either one or the other will give, first of all, one problem, one challenge. What kind of time step needs to be used to integrate the equations? The answer, or at least one suggestion, is given in the text, one rule of thumb. And then another, the model superposition is shown, meaning that before running the dynamic analysis we need to run a normal mode analysis, because the model superposition technique uses the modes. And then how many modes we have to consider in the superposition, and the answer is given by the effective modal masses. Rule of thumb again there is to use at least 85% of the total mass, where with mass we mean mass and moments of inertia. And it is shown what happens if not enough modes are used. In the response, some peaks are clearly not considered. So we need to be careful when we run superposition model analysis to use the correct number of modes. And here some hints are given on when to use one or the other solution. Then the other approach, or the other analysis that can be found to be solved, to be done, is the one with a time history of forces. So we take the same beam, and now we have two forces which are acting in two different directions, and with this time history. So it increases, then it stays. Clearly this is quite quick, and then they just go out, and we see the response of the structure. Again, some advices are given on what time step to be used, because this is quite easy to be understand. Of course, we need that the time step is enough to be able to follow the time history of the forcing. But in this case, clearly we need to have a very small one, because the time history is quite complex. Okay, then we switch to this one. We solve the problem. Then we look for the maximum stress and the displacement. So what is the time history of the response? And with the direct integration, then we switch to the model superposition. We look on the effective model masses to see if we have enough, if we think we have enough. And then we compare the results. There is a difference, which is engineering-wise not so huge in terms of stress, and even less in terms of displacement. And yeah, then that's it. Other comparisons are done, trying to match better by increasing the number of modes to be considered into the modal superposition approach. And finally, the difference between the two techniques ends when we have to enter nonlinearities, in the sense that the modal superposition technique can be used only for linear models, so no contacts, no big displacements, no material nonlinearities. If we have one of the three, then the only way to solve it is using the direct integration approach. And we show here what is happening when we enter into plasticity by having this bilinear material behavior. In terms of displacement, there is no big difference, but in terms of stress, there is quite a lot, especially in the rundown, so to say, where clearly the stress are different because we have some residual stresses coming from the first yielding of the material. And then explicit methods are okay. Some words are spent on spectrum analysis, random vibration analysis, but these are so peculiar that only few notes are given here. Then explicit methods are discussed. What is mainly why they are called explicit, and so the equations that are governing the explicit approach are shown here. And the same example as before is used and compared with the implicit approach, seeing that there is not so many differences. So also in terms of computational time, the comparison between the two is given. And some discussion are given on the time step here to integrate. This is not really something arbitrarily chosen like it could be for the implicit approach, but there are some rules that need to be respected, and here is explained why. And it could be that some problems that cannot be solved with the implicit approach might be solved with the explicit, like the example we have seen in chapter 13 of the 3D gasket, which needs to be pressed into the housing, can be solved. So the explicit code will always give you some results. Then it depends on the quality of them. Here we see there are some distorted elements which might tell or suggest that the solution is not the right one. But at least we see something, and we can decide maybe to increase the mesh size, decrease the mesh size, so increase the refinement of the mesh, and run it again. So we might come to results that are at least acceptable, whereas with the implicit method this was not possible at all. Okay, we leave this topic, and as you already can see here, next one will be structural optimization. So see you the next time. Bye bye.